I guess we can get started. We're going to start chapter 5, section 2, sequences in mathematical induction and recursion. Mathematical induction, part 1, proving formulas. In natural sciences, deduction and induction are presented as alternative modes of thought, deduction being to infer a conclusion from general principles using the laws of logical reasoning, and induction being to enunciate a general principle after observing it to hold true for a large number of specific instances. Discovery of new mathematical facts often occurs through experimentation with examples, but mathematical induction as a proof technique is not inductive but deductive. Once proved by mathematical induction, a theorem is known just as certainly as if it were proved by any other mathematical method. The principle of mathematical induction: let P of n be a property that is defined for integers n, and let A be a fixed integer. Suppose the following two statements are true. P of A is true. For every integer k greater than or equal to A, if P of k is true, then P of k plus 1 is true. Then the statement, for every integer n greater than or equal to A, P of n is true. So you prove that the basis instance is true, and then you prove it that it's true for various other subsequent instances. First known use of mathematical induction occurs in the work of the Italian scientist Francesco Moralico in 1575. In 1653, Pascal gave a clear description of the technique. In 1883, De Morgan, best known for De Morgan's laws, gave the process the name mathematical induction. An equivalent logical inference rule known as the well-ordering principle. To visualize the idea of mathematical induction, imagine an infinite collection of dominoes positioned one behind the other in such a way that if any given domino falls backward, it makes the one behind it fall backward also. Then imagine that the first domino falls backwards. What happens? Well, they would all fall down. So if the kth domino falls backward, it pushes the k plus 1 domino backwards as well. To see the connection between this image and the principle of mathematical induction, let P of n be the sentence, the nth domino falls backwards. It is given that for each k greater than or equal to 1, if P of A is true, the kth domino falls backwards, then P of k plus 1 is also true. It is also given that P of 1 is true, that the first domino falls backwards. Thus, by the principle of mathematical induction, P of n, the nth domino falls backwards, is true for every integer n greater than or equal to 1. Proving a statement by mathematical induction is a two-step process. The first step is called the basis step, and the second step is called the inductive step. Method of proof. Consider a statement of the form, for every integer n greater than or equal to a property P of n is true. To prove such a statement, perform the following two steps. Step 1, the basis step. Show that P of A is true. Then the inductive step. Show that for every integer k greater than or equal to a, if P of k is true, then P of k plus 1 is true. To perform this step, suppose P of k is true, where k is any particular but arbitrarily chosen integer with k greater than or equal to a. This supposition is called the inductive hypothesis. Then show that P of k plus 1 is true. All right. Use mathematical induction to prove that 1 plus 2 plus 3 plus yada 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 to n equals n times n plus 1 over 2 for every integer n greater than or equal to 1. Okay? To construct a proof by induction, you must first identify the property. In this case, P of n is the equation 1 plus 2 plus 3 and so forth to plus n equals n times n plus 1 all over 2. Note, this property is just the equation. The proof will show that the equation is true for every integer n greater than or equal to 1. Note that the subject of the sentence is the sum of the integers from 1 to n, and its verb is equals. So it is a proper sentence. In the basis step of the proof, you must show that the property is true for n equals 1, or that P of 1 is true. Now, P of 1 is obtained just by simply substituting n in place of 1 in place of n in the equation. The left-hand side of P of 1 is the sum of all successive integers starting at 1 and ending at 1. This is just 1. Now, so you show that this is 1 and times 1 plus 1 all over 2 is, of course, equal to 1 as well, which equals the left-hand side of the equation. In the inductive step, you assume that P of k is true for a particular but arbitrarily chosen integer k. This is the inductive hypothesis. You must then show that P of k plus 1 is also true. What are P of k and P of k plus 1? Well, P of k is obtained by substituting k for every n in P of n. Thus, P of k is this. That's the inductive hypothesis. Similarly, P of k plus 1 is obtained by substituting the quantity k plus 1 for every n that appears in P of n. Thus, P of k plus 1 is this equation, or equivalently, here. Okay? Now, the inductive hypothesis is the supposition that P of k is true. How can this supposition be used to show that P of k plus 1 is true? P of k plus 1 is an equation, and the truth of an equation can be shown in a variety of ways. One of the most straightforward is to use the inductive hypothesis along with algebra and other known facts to separately transform the left-hand side and right-hand sides until you see that they are the same. So, in this case, the left-hand side is 1 plus 2 plus 3 plus, and so on to k plus 1, which equals 1 plus 2 plus whatever, and so on to plus k plus 1. Substituting from the inductive hypothesis, you get k equals k times k plus 1 over 2 plus k plus 1. Now, multiply the numerator and denominator of the second term by 2 to obtain a common denominator. By adding the fractions with the same denominator and combining terms, you get this. So the left-hand side is k squared plus 3k plus 2 over 2. Now the right-hand side of p of k plus 1 is k plus 1 plus times k plus 2 is by multiplying out the numerator. You can see that the both sides k plus 1 are equal. The two sides of p of k plus 1 are equal to each other. So the equation p of k plus 1 is true. So the sum of theorem 521. The sum for the first n integers, for every integer n is greater than or equal to 1. 1 plus 2 plus 3 to n is equal to n times n plus 1 all over 2. Definition. If a sum with a variable number of terms is shown to equal an expression that does not contain either an ellipsis or a summation symbol, we say that the sum is written in closed form. All right. So applying the formula of the sum for the sum of the first n integers, what is 2 plus 4 plus 6, yada, 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 to 500? It'll just be 2 times n times n plus 1. You'd factor out the 2 to get 2 times 1 plus 2 plus 3 plus 4, so on and so forth, to 250, and then use the equation from there. And then for 5 to 50, you would do the sum of the numbers from 1 to 50, and then subtract the sum of the numbers from 1 to 4, and so forth. All right. So 62,750 for the first equation, 1265 for the second equation, and to do 1 plus 2 plus 3 to h minus 1, substitute h minus 1 in there for n and multiply it out, reduce it down, and it comes to h minus 1 times h over 2. All right, another famous and important formula in mathematics, the formula for the sum of a geometric sequence. In a geometric sequence, each term is obtained from the preceding one by multiplying a constant factor. If the first term is 1 and the constant factor is r, then the sequence is 1, r, then r squared, then r cubed, then rn, and so on and so forth. The sum of the first n terms of this sequence is given by the formula. The summation of I equals 0 to n, r raised to the I power, is r to the n plus 1 minus 1 all over r minus 1. For every integer n greater than or equal to 0, and every real number r not equal to 1. The expanded form of this formula is here. And because r of to the raised to the 0 power is equal to 1, and r to the first power is r, the formula for n greater than or equal to 1 can be rewritten as this here. In some mathematical contexts, 0 to the 0th power is regarded as an indeterminate. In discrete mathematics, we usually define 0 to the 0th power as equal to 1. So that when we have the summation of I equals 0 to n of r to the ith power, we do not need to give special attention to the case r equals 0. All right. Prove that the equation is true for the sum of a geometric sequence for every integer n greater than or equal to 0, and every real number r except for 1. In this example, the property p of n is again an equation, although in this case it contains a real variable r. Because r can be any real number other than 1, the proof begins by supposing that r is a particular but arbitrarily chosen real number not equal to 1. Then the proof continues by a mathematical induction on n, starting with n equals 0. In the basis step, you must show that p of 0 is true. That is, you show the property is true for n equals 0. So you substitute 0 for each n in p of n, like this. In the inductive step, you suppose k is any integer with k greater than or equal to 0, for which p of k is true. That is, you suppose that the property is true for n equals k. So you substitute k for each n in p of n. Okay? Then you show that p of k plus 1 is true. That is, you show the property is true for n equals k plus 1. So you substitute k plus 1 for n, or equivalent in this form, or equivalently here. And you get the I didn't show the proof, did they? Proving an equality. The proofs of the basis and inductive steps illustrate that two different ways to show that an equation is true. One, by transforming the left side and the right side independently until they are seen to be equal. And two, transforming one side of the equation until it is seen to be the same as the other side of the equation. So, sometimes people use the method that they believe proves the equality that is actually invalid. For example, to prove the basis step for theorem 522, they perform these steps. This isn't apparently valid. So, deducing additional formulas. The formula for the sum of a geometric sequence can be thought of as a family of different formulas in R, one for each real number R except for 1. And if each of A and B below, assume that M is an integer that is greater than or equal to 3. Write each of the sums in closed form. So r is equal to 3, and you're going from 0 to m minus 2, and oh yeah, the 3 to the m minus 2 plus 1 minus 1 over 3 minus 1. So it would be 3 to the m minus 1 over 2. The second one would be 9 times the, we factor out the 3 squared, and you would get this equation here. As with the formula for the sum of the first n integers, there is a way to think of the formula for the sum of the terms of a geometric sequence that makes it seem simple and intuitive. Let S of n equal 1 plus r squared plus so on and so forth. Then r to the s sub n is r plus r squared plus r to the third, and so on to r to the n plus 1. And then r to the r times s of n minus s of n is this here. And then when you simplify it, it becomes r to the n plus 1 minus 1. Okay? So, deducing additional formulas. Equating the right side of the equations of 521 and 522 and dividing by r plus 1 or minus 1 gives s of n. S sub n is r to the n plus 1 minus 1 over r minus 1. And that will conclude that set of slides. And another brief set here. Section 3, Mathematical Induction, Part 2, the applications of it. This section will show how to apply it in a broader variety of situations. As a first example, consider the argument that the US penny should be eliminated because it isn't profitable to produce. Due to inflation and the rising cost of metals, it actually costs more than 1 cent to produce a penny. If the penny were eliminated and another coin worth 3 cents were introduced, what prices could be paid using only 3 and 5 cent coins? The table below shows some examples. Well, that's not all of them. They don't have the 3 cent plus 3 cent to make 6 cents. But you can see after 8 cents, all values can be obtained by using a 3 and 5 cent piece. For every integer n greater than or equal to 8, n cents can be obtained using only 3 and 5 cent coins. Use mathematical induction to prove that for each integer n greater than or equal to 0, 2 to the 2n power minus 1 is divisible by 3. Okay? So As in the previous proofs by mathematical induction, you need to identify the property n. In this example, that is 2 to the 2n minus 1 is divisible by 3. By substitution, the statement for the basis step, p of 0, is 2 to the 2 times 0 minus 1 is divisible by 3. The supposition for the inductive step is p of k is p to the 2k minus 1 is divisible by 3. That's the inductive hypothesis. And the conclusion to be shown, p of k plus 1, is p of 2 to the 2k plus 1 minus 1 is divisible by 3. Recall that an integer m is divisible by 3 if and only if m equals 3r for some integer r. Now the statement p of 0 is true because 2 to the 2 times 0 power is 2 to the 0, which is 1, minus 1, which is 0, which is divisible by 3. All right? Prove the inductive step. You suppose that k is any integer greater than or equal to 0, such that p of k is true. In other words, you suppose that 2 to the 2k power minus 1 is divisible by 3. You must then prove that the truth of p of k plus 1 is also true. Thus, you must show that p of 2 to the 2 times k plus 1 minus 1 is divisible by 3. Now, you can expand this out by the laws of exponents and use a little bit of algebraic magic here. So now your aim is to show 2 to the 2k times 4 plus minus 1 is divisible by 3. Why should that be so? Both 2 to the 2k times 4 minus 1 and 2 to the 2k minus 1 have a lot in common. And by the inductive hypothesis, 2 to the 2k minus 1 is divisible by 3. Observe when you subtract 2 to the 2k minus 1 from 2 to the 2k times 4 minus 1. You get this, which you don't know if is divisible by 3, but that is divisible by 3. That is divisible by 3. Adding 2 to the 2k minus 1 to both sides, you get 2 to the 2k times 3 plus 2 to the 2k minus 1, which this is divisible by 3, and this is divisible by 3. And since the sum of two numbers that are divisible by 3, you can conclude that the whole right-hand side is divisible by 3. So the sum is divisible by 3, therefore the left-hand side of the equation is also divisible by 3, which is what is to be shown. Now, use mathematical induction to prove that for each integer n greater than 3, 2 to the, this is a typo, 2n plus 1 is less than 2 to the n. That is supposed to be 2n, not 2 to the nth. Error in the slides here, and they repeat it several times. In this example, so here they get it right. The property p to the n is the inequality. 2n plus 1 is less than 2 to the n. By substitution, the statement is for the basis step, p of 3, is 2 times 3 plus 1 is less than 2 to the third power. The supposition for the inductive step is 2k plus 1 is less than 2 to the k. And the conclusion to be shown is 2 to the k plus 1 is less than 2 to the k plus 1. To prove the basis step, observe that the statement P of 3 is true because 2 times 3 plus 1 equals 7, and 2 to the third equals 8, and therefore 7 is less than 8. For the inductive step, you assume that the inductive hypothesis for that for a particular but arbitrarily chosen integer k greater than or equal to 3, 2k plus 1 is less than 2 to the k. And then you must show that 2k plus 1 no, 2 to the 2 times 2k 2 times k plus 1 is less than 2 to the k plus 1. So, yeah, down here. This is another typo. These slides are produced by the company that did the book, but not very well. At this point, you need to think about your goal. You want the right-hand side of the inequality to be 2 to the k plus 1. Since you already know that 2k plus 1 is less than 2 to the k plus 2, easy way to complete your job would be to show that 2 to the k plus 2, 2k plus 2 is less than 2 to the k plus 1. But this inequality is true because 2 is less than 2 to the k for all k greater than or equal to 3. And thus, these typos are getting to me. I needed to straighten this out. Anyway, by algebra and law of exponents, transitivity of order of order, that implies that 2k plus 1 is less than 2 to the k plus 1. And this screen shows the slides wrong. So when you look at the slides on Canvas in PowerPoint, they will show up correctly and they won't be overlapping text and all that sort of stuff. So proposition 533, for every integer n greater than or equal to 3, 2n plus 1 is less than 2 to the n. Proving a property of a sequence. Define a sequence of A1, A2, A3 as follows. A1 equals 2. A sub k equals 5a sub k minus 1 for every integer k greater than 2. So write the first 4 terms of the sequence. Well, it would be A2 would be 10 because A1, it would be A2 minus 1 is 1 and A1 is 2, so it would be 10. 3 would be 5 times 10. If k is 3, a sub 3 would be 50. 10 times 5, and so on and so forth. It is claimed that for each integer n greater than or equal to 0, the nth term of the sequence has the same value as that given by the formula 2 times 5 to the n minus 1. In other words, the claim is that the terms of the sequence satisfy the equation a sub n equals 2 times 5 to the n minus 1. Prove that this is true. Well, the sequence seems to hold true here. The 2, 5, or 2, 10, 50, 250, and so on. To use mathematical induction to show that every term of the sequence satisfies the equation, begin by showing that the first term of the sequence satisfies the equation. Then suppose that an arbitrarily chosen term, a sub k, satisfies the equation, and prove that the next term also satisfies the equation. So let this be the sequence defined by specifying that a1 equals 2 and a sub k equals 2a sub k minus 1 for every integer k greater than or equal to 2. And let the property p of n be the equation given here. So we'll use mathematical induction to prove that for every integer n greater than or equal to 1, p of n is true. First, show that p of 1 is true. By simple substitution, multiplying things out, you get a of 1 equals 2. And the right-hand side, substitute around and multiply it out, and you get also 2. By the definition of the sequence and by mathematical processes. Thus, the two sides of P1 are equal to the same quantity, and hence P1 is true. Show that for each integer k greater than or equal to 1, if P of k is true, then P of k plus 1 is also true. Let k be any integer with k greater than or equal to 1. And suppose that a sub k equals 2 times 5 to the k minus 1. We must show that p of k plus 1 is true. Must show that a sub k plus 1 equals 2 times 5 to the k plus 1 minus 1. Or equivalently, a sub k plus 1 equals 2 times 5 to the k. But the left-hand side is a sub k plus 1 minus 1, which is 5 times k, a to sub k. So by inductive hypothesis, you can substitute in 2 times 5 to the k minus 1 times 5, regroup and rewrite, and then which is the right-hand side of p of k plus 1, as was shown below, or above, or before. Since we have proved the basis step and the inductive step, we conclude that the formula holds for all terms of the sequence. Now a little toy game type of thing from the people that brought you Tetris. A problem with trominos, or whatever. The word polyomino, a generalization of domino, was introduced by Solomon Golem in 1954 when he was a 22-year-old university student. Subsequently, he and others proved many interesting properties about them, and they became the basis for the popular computer game Tetris. A particular type of polyomino, called a triomino, is made up of 3 attached squares, which can be of 2 types, straight and L-shaped. Call a checkerboard that is formed by using m squares on a side, an m by m checkerboard. Observe that if one square is removed from a 4x4 checkerboard, the remaining squares can be completely covered by L-shaped triominos. For instance, a covering for one such board is illustrated in the figure below. So they were able to prove for any integer n greater than 1, if one square is removed from a 2 to the n by 2 to the n checkerboard, the remaining squares can be completely covered by L-shaped triominos. And that is it for that one. I don't know if we have enough time to cover another section, so I'm going to stop it at this point. Anyway, have a good day. See you on Thursday.